I was asked to say a few words about why I'm here, why I was chosen to moderate this session, and also how I kind of got into this position. And I am a volunteer now for the Citizens Climate Lobby, and I'm going to talk at the end of this session a little bit more about the detail of Citizens Climate Lobby. And there's actually invitations to all of you who are from Western Maine to come to our training on June 24th, and there's little invitations you can pick up in the back. So we'll talk more about that later, but how I got to Citizens Climate Lobby, it's kind of I'm going to tell that story in brief, very brief. And that is, I'm an aquatic ecologist. I've been working in lake assessment and lake protection in Maine for going on to 3 decades. And I not only do assessment work, but I also work for an organization that trains citizen scientists to collect this critically important scientific data on the health of our lakes. As a result of this group of well-trained volunteers that are operating all across the state of Maine, Maine has a very robust set of data about our lakes. We understand the status of our lakes now. We understand the trends in the directions that some lakes are moving and others maybe not so much. And we understand the impacts of some of the threats to our lakes, and we see them playing out, not the least of which is climate change. So I can't go into all the details on those lakes, but just to say that unabated, if we continue on the trajectory that we're on with climate change, our lakes are going to be not the cleanest, clearest lakes in the world like they are now. They're going to be warmer, they're going to be greener, they're going to be more susceptible to invasive species, they're going to be more susceptible to harmful toxic algal blooms, blue-green algae, many of them that produce algal toxins, like the warmer water, and so on. So our lakes are really at risk of changing in a way that none of us want to see them change. And as a result of those changes, and from in other ecosystems as well that are going to really be significantly harmed by the warming climate, many of our critters, and I was just so delighted to hear about all of the critters that have returned to Androscoggin River. All of that good news, all of that good work is going to be kind of reversed by this trend in climate change. So these are some of the critical creatures that are kind of at the top of the list of being most vulnerable to the changing climate. So as a scientist, I have been lucky to be part of taking action with regard to 2 of the important legs of the stool, if you will, of addressing climate change. One of those is the assessment piece, understanding where we are and how things are changing in response to climate change. The second leg of the stool is adaptation. What can we do to minimize the impacts of climate change? And for example, we work with volunteers to understand the issues in their watershed that could be leading to excess nutrients running into lakes and so on. Much of the infrastructure built to manage the flow of water through our watersheds, culverts, ditches, and so on, with the new changing climate and more frequent extreme weather events, though that infrastructure is no longer adequate. So we're working on that piece as well. But it's that third leg of the stool, without which the stool is not going to stand up, and that is mitigation. Reeling back in the carbon, that is the CO2, that is causing the climate change. I've been frustrated as a resource manager in that when I go to conferences and I are part of a webinar, there's a lot of discussion of the adaptation piece. How are we going to adapt to these changes? Almost no discussion of the mitigation. How can we change that situation? How can we change the trajectory that we're currently on with regard to carbon emissions? And that frustration mounts in me as a person. I'm a mother, I'm a grandmother, and I'm looking out to future generations. And at that point, my frustration becomes heart-wrenching. So that has been my issue, and that's the context in which I came upon the Citizens Climate Lobby. And it was Peter Garrett that introduced me to Citizens Climate Lobby, and I'm going to tell you more about it later, but I just want to say that it has given me tremendous hope. And I feel like now I'm part of that action to create a good third stool, the third leg of our stool. And I really think that we can make a difference. We have time to still make a difference, and I'd like any of you who'd like to learn more about it to pick up a brochure or pick up the invitation in the back and come to our meeting and get engaged. And I will tell you a little bit more about Citizens Climate Lobby's approach. It's very straightforward. Their vision is a livable world. They have a very straightforward way of accomplishing that. It's a bipartisan way of accomplishing that. It's purposefully bipartisan. And so it's a pretty exciting initiative. It's making progress, and I hope that a few of you will stay after the talks, which I'm very excited to hear, to learn more about Citizens Climate Lobby. So with that, having said that, I think we can get rid of my slides. I don't know who is pulling up the next, but we do have two speakers, and so great to have two speakers speaking about the climate here today. And the first is Chris Kimball. And he is a meteorologist for the National Weather Service. And he'll... Switch the order? Well, I thought we did switch the order. Did we? Yes? No? Did we? I thought you said yes. Is this right? Chris first? Is that okay? Or no?
Well, if Chris is first, I have to...
Okay, never mind then. We are going to go back. So, our first speaker, sorry about that, Chris. You have to wait a bit. Is Dr. Lindsay Rusted. And Dr. Rusted is a research ecologist and co-director of the USDA Northeast Climate Change Hub. She's also a team leader of the Hubbard Brook Experimental Forest, one of the longest standing study sites, which is in New Hampshire. And she'll have about 25 minutes to speak, and we'll have some time for questions as well. So, handing over the mic to Dr. Rusted.
Okay, so I guess I get to go first.
I guess you do.
Okay.
This is...
Sorry about that, it was a little technical issue. Oh, you were just testing us.
There you are.
Here's your slide advancer.
And I will give you a little cue when you're down to the 5-minute mark, if that's helpful for you.
That would be great.
The right is...
Sure. Okay, it will be tricky if I cannot trip on this because I do like to pace. So good afternoon. My name is Lindsay Rusted. I am a research ecologist with the USDA Forest Service, and I am the team leader for the Hubbard Brook Experimental Forest. I am a Maine resident. I live in Cumberland, Maine. We have a summer place up in the Rangeley area. I work in the White Mountains and in Durham. So this is certainly an area I'm very familiar with and is very near and dear to me. I have actually been studying climate change and its impacts on the northern forest ecosystem for over 25 years. Kind of hard to believe. But so it's been very interesting to see kind of the increase and the development of our understanding of climate change and its impacts. And I work at 3 different levels. My favorite is I love to do experiments. I do big experiments. I like to warm ecosystems and drought ecosystems and do ice storm experiments to see how a system is going to respond and study the forests of tomorrow today. I also do a lot of work of synthesizing different experiments across the world. So I get to work with colleagues from all over the world. And then the third thing I like to do is I like to bring people together. I like to bring people together in networks to share knowledge. And so what I'm going to talk about today is one of those efforts. And it's this publication that we did a number of years ago called Changing Climate, Changing Forests. And in this, we brought together 50 or 60 of my closest friends and colleagues in New England and southern Canada to share everything that we knew about climate change impacts on hydrology and wildlife and forests and pests and pathogens and biogeochemistry. There was a lot of information that was scattered around, and we felt that it was really important to to bring it together. So we did this, and then I also want to just point out that hot off the press, we did an update on this, a little bit more technical, but it's an update of an evaluation synthesis of what we know about climate change in New England and Canada. So I always like to set the stage about, so what I'm going to talk about today is changing climate, changing forests, and really focus on the regional impacts. But to do that, I always feel like I need to set the stage at a global level, and I promised Ferg that I would not talk about the global scale too much. But I thought it was important to just kind of set the stage and that we know unequivocally, right, that atmospheric greenhouse gases, CO2, methane, nitrous oxide, have been going up since the beginning of the Industrial Revolution. We know unequivocally that global temperature, surface temperature, and ocean temperatures are going up. We can measure that. We know unequivocally that precipitation patterns across the world have changed. Some areas are seeing more precipitation, some areas are seeing less. We know with the increase in temperature, we're having a decline in land and sea ice. And as we have more of that water go into the seas, we know that we're having sea level rise, both from the fresh water, but also from thermal expansion. Again, these are all things, we have a lot of data we can measure. We know the oceans are acidifying, right? This is high school math and science. CO2 is a weak carbonic acid. The oceans, as it dissolves into the water, has to acidify. And then the other thing that's been harder to get a handle on is extreme events and the attribution of extreme events to climate change. But we've learned a lot about this and are making great strides in understanding extreme events. So those are things that we know about the history of climate change at a global scale, and I'm just going to put this one graph up here. I'm sure that you're all familiar with it. It's atmospheric CO2 concentrations. We're at about 275 parts per million before the Industrial Revolution. When Sir Charles Keeling started measuring this, it was 315 in 1958. We're now at about 410, and if we keep going as business as usual, we're going to get up to 800 or 900 parts per million. Over here's the concomitant change in temperature, 2 to almost 7 degrees Fahrenheit. So again, this is based on the best available models coming forward. So you say, well, that's a global scale. What we're really here to talk about is our backyard. So on a regional scale, our synthesis looked at the 5 New England states, New York, and the eastern Canadian provinces. And we did this because climate change doesn't know political boundaries, right? It doesn't know when you go into southern Ontario. So we thought it was very important to work with our Canadian colleagues. And I want to tell you that the amount of information available is inversely proportional to the area. So there's not a lot of data from Canada, but we tried to dig out as much as we can. I'm also going to talk a lot about our data from the Hubbard Brook Experimental Forest that we talked about. Has anybody been to the Hubbard Brook Experimental Forest or know about it? Well, it's over about 60 miles from here in the White Mountains of New Hampshire. It's basically was established in 1955, over 60 years ago, as a center for hydrologic research, and it's since grown to be one of the longest, continuously running, perhaps most famous or infamous long-term research sites in the world. And we have people coming all over the world to come do work at Hubbard Brook, to visit Hubbard Brook. So it's a really special place. It's about an 8,000 acre experimental watershed. We measure all the inputs in precipitation, all the outputs in stream flow, and by difference we can begin to understand, take apart the black box of what's going on in ecosystems. We're also the site of some of these large watershed studies. And again, just some highlights, acid rain. You guys remember acid rain? It's a great environmental success story. We actually now study the recovery from acid rain. We've done a lot of work in responsive forests to whole tree harvest. We have some of the longest running migratory bird studies in the world at Hubbard Brook. We're celebrating 50 years of bird studies now. Winter biogeochemistry, and of course the impacts of climate change and extreme events on our forests and ecosystems. So at Hubbard Brook, one of the things that's interesting is we don't just have temperature and precipitation. We have all these different indicators of climate change. So we have meteorologic studies that go back over 60 years. We have soil studies, temperature and moisture and frost. We have biological, phenology, birds, vegetation, and hydrological. I can't go through all of these, but I will touch on some of this because it's such an important long-term record. So again, starting in about 2010, we felt that it was really important to bring together this growing body of knowledge about climate change. And as scientists are, we brought them together and we wrote these 5 very dense technical papers. And then all my scientists went away and they went back to their work, and I was kind of left, and I said, gee, we really need to translate this so other people can have access to it. So it's kind of like the 3 bears. I first worked with a science writer where it was too technical, and I literally threw all of that away. And then I worked with a science writer where it was too non-technical. And then I finally worked with a science writer who I think we got it kind of just right. So that's this publication, but it's important to know that it's based on this body of scientific work. And so today I'm going to talk about climate and hydrology, forests, and wildlife. I won't have time to talk about past pathogens and invasives, or kind of my favorite, which is biogeochemistry. But I just want you to know that those are out there. So we started by posing these questions. So questions on how are the climate and hydrology of the Northeast changing? How are Northeast forests responding to that change in climate? How are wildlife in Northeast forests responding to climate? And even though we're not policymakers, we couldn't not at least address what are the implications for policy. So we took the same approach for all these papers. We're scientists, so we start with first principles. What do we think we know? What do we think will happen? And then we looked into history, and we said, what do we know about how things have changed here in New England? Again, not across the globe, but here in our backyard. And then what's the best of future predictions? So the first one is climate and hydrology. And we started by saying, well, where do we fit with the rest of the world? So if you're familiar with looking at climate science, this is called a temperature anomaly. And basically we take this 0 line, which is the mean temperature from 1951 to 1980. And if the annual temperature is lower than that mean, it's negative. It's higher than that mean, it's positive. And so this is kind of a typical graph of how temperatures have increased over time. Lots of noise. So on a global scale, we've seen about a 1.5 degree Fahrenheit increase in temperature. Continental scale, 1.6, and here in the Northeast, 1.4. So just to say, we're not an anomaly. We're kind of going along with what the continent and what the globe is doing. So based on the work by these authors, Tom Huntington, USGS, and Catherine Hayhoe, we can see that in our area, we've seen an increase over the last 100 years of 1.4 degrees Fahrenheit. Winters are warming the most. We've actually seen more precipitation, about 9% increase in precip, more intense precipitation. More of our precipitation is coming in these really big events. Longer growing seasons, less snow and ice. Now I know it's hard to see in the back, so you're just going to have to trust me. So these are data from Hubbard Brook, and at Hubbard Brook over 60 years, very careful, meticulous records, we've actually seen an almost 3 degree Fahrenheit increase in temperature. Our winters have definitely warmed the most. We've seen a 4 degree Fahrenheit increase in temperature in the winters, and it's our minimum temperatures that are warming the most. So those of us who've been around for a while and we say, winters aren't as cold as they used to be, we have data from 60 years of at Hubbard Brook that show that this is actually the case. In terms of water balance, again, you can't see on this screen, but basically at Hubbard Brook, we're seeing an increase in precipitation, increase in stream flow. Stream flow is actually increasing more than precipitation, so we have a decrease in evapotranspiration. And that's kind of peculiar because it's getting warmer, so you would think you'd have more evaporation, but we think that we have actually more clouds. And of course, this is something that we haven't monitored over the decades. In terms of precipitation at Hubbard Brook, we see a whole foot more of precipitation than we saw back in the 1950s. So that's a lot. And then this is binned by decade, and the bars are just what levels, 0 to 1 inch, 1 to 2, 3 to 4. And what we find that most of our increase in precipitation is not the really big events, but the 1 to 2 inches, those soaking rains. We can show that we are having more of those, and that's what's contributing to the foot more of precipitation. Snowpack. We're all tired of snow, but I think most of us love snow here in New England. We've measured several metrics of snowpack, and all of them show about a 25% decline in our snowpack. This one shows a decline in maximum snow depth. We've lost about 10 inches over 60 years, and this is the number of days with snow cover. So we've lost 21 days of snow cover at Hubbard Brook. And then, of course, ice. The day that ice goes in is coming later. The day that ice goes out is coming earlier, and we have 19 days less of ice cover. So again, these are things that we all say, we think this is happening, and we have some good data from different lakes and watersheds, but this is a long-term record, same methods for 60 years. So, New England river and stream hydrology. We have observed increases in average stream flow, earlier spring high flow, earlier snowmelt, higher flood flows. At Hubbard Brook, again, we see this. This is just high flows for 2 of our small watersheds, just seeing an increase in those high flows over time, and those same 2 watersheds, a decrease in the low flows, again, reflecting the greater amount of precipitation that we're getting. So we can say that the 20th century in our backyard is indeed becoming warmer and wetter. So if we look to the future, this is some very sophisticated climate modeling work that was done by Catherine Hayhoe, who was one of Time Magazine's 100 most important people a couple of years ago for her climate work. So she basically uses these statistical downscaling methods. They're based on lots of models and emission scenarios, spatial resolution of 12 kilometers, and they create this daily output that then they do an input into other models. And anybody who wants to ask me about that, you're welcome to. But you can just kind of rest assured it's some of the best statistical modeling that we have. Again, I know you can't really see this in the back, but her projections suggest that we will see another 5 to almost 10 degrees Fahrenheit increase in temperature by the end of this century. Summers now will be warming most. Remember, before it was winters were warming most. Another 7 to 14% increase in precipitation, more intense precipitation, more energy, right? So more intense precipitation events, longer growing seasons, greater than a month longer in growing seasons, and a decrease or an elimination of the snowpack. You guys might have seen this figure. It was created by the Union of Concerned Scientists, and it just shows, at least for New Hampshire, under a low emission scenario, our climate may begin to look like that of Baltimore, Maryland, and under a high emission scenario, it may start looking like Virginia. So again, these are what the models are suggesting. And then overlaying on all of this is more variable, extreme, and unpredictable weather. In terms of river and stream hydrology, the projections are a continuation of those observed trends, right, of high flow and low flow. The difference is because we have the highest temperature in the summer, not the winter, we actually expect more droughts and more low flows, despite the fact that we have more precipitation. So we expect more low flow condition and, of course, warming of the surface waters. and continued increase in extreme weather events. So our future predictions are that the climate of the region is likely to become warmer and wetter, but ironically also drier. I'm doing drought experiments at Hubbard Brook. How is drought going to impact our forests? People think I'm crazy, but if you look at the models, we expect more droughts. So how is this all affecting the forest? So we had a whole paper on this that was led by Jackie Mohan, Roger Cox, and Louis Iverson, who's very well known in this field. First principles. Okay, we know forests change, right, in response to a changing climate. We're not dumb, right? And we know that forest composition shifts in response to a slowly changing climate. And we know that the suitable habitat, the kind of habitat where these trees grow best, is likely to move north in latitude and up in elevation. But we also know that species have trouble keeping pace, reproduction, dispersal, migration. They're not going to just pick themselves up by the roots and march north or march up. They have trouble keeping up with this rapidly changing climate. So we've done a lot of work to try and figure out on the landscape, our historical perspective, if we can see changes in the landscape. And in 2008, Becky et al. Said, we got it. We saw this upward shift, right? You can see this in the northern hardwood to boreal forest ecotone, about 100 meters. And we said, we're seeing climate change on the landscape. But if you wait long enough in science, someone will come along and kind of prove you wrong. And Foster and D'Amato said, that wasn't really true. There were other things coming along. We haven't really been able to see this in other parts of New England. So the jury is out whether we're really seeing these shifts in landscape. And there's so many other things, recovery from acid rain and mercury and change in land use. So it's a very complicated pattern. So forest productivity, forest products industry cares deeply about this. We would expect increased productivity due to warmer temperatures, longer growing seasons, CO2 fertilization, and nitrogen fertilization. We still have a lot of nitrogen coming in our deposition. On the flip side, we would expect decrease in productivity due to extreme climatic events, nuisance species, which I talk about as pest pathogens and invasives that tend to do better under a warming climate. We still have acid rain, nitrogen saturation, ozone, and drought. So there are these conflicting patterns that we're trying to tease apart. If we look into the past, however, we know that there have been tree declines associated with climatic events, and we list them here. But to simplify, we know that in the past we'd have birch and sugar maple declines with extended winter thaws. We know that red spruce has shown decline with late freeze, freeze-thaw, and oak and ash are particularly susceptible to drought. So we can look in the past and we say that some of these conditions have caused changes in the productivity of our forests. So what about the future? Okay, Louis Iverson has worked on the tree atlas. And again, he does this very sophisticated statistical manipulations where he basically develops these relationships between where tree species are right now, and what the climate is, soils, topography, land use. And then he goes and he went and worked with Catherine Hayhoe and took her models to project what the climate was going to look like, and then said, well, we know where the trees should be, what's a suitable habitat in the future? So it's not necessarily where trees, again, are going to pick up their roots and march north, but it's a kind of habitat that's most conducive to these species. And to the extent that the species are outside of their suitable habitat, they're going to be more stressed. So these are some of the model projections. Again, suitable habitat by the end of this century. These were for 84 tree species. And if we just look down here, the average we expect for common tree species, about an even decrease in suitable habitat for some, increase in others. I really like to think of winners and losers. I try not to be completely a naysayer and say, yep, we might lose some of the suitable habitat for our iconic species of spruce, fir, sugar maple, birch, northern white cedar, but there are winners, oaks and pines. So in terms of forest products and productivity, we're still going to have trees on the landscape. Another way to look at this is not by individual tree species, but by forest types. And so here's a map, if you can see this, of the current distribution of forest types. This is under a low emission scenario by the end of the century. This is a high emission scenario. The blue is spruce fir. And you can see this is where you would expect to find spruce fir. It kind of begins to disappear under the low emission scenario, is virtually gone in the high emission scenario. The magenta is our lovely beech birch maple. And you can see this is where we find it now. We might see an expansion over the low emission scenario, but a loss in the high emission scenario. And most of this is going to be taken over by oaks and pines. Again, suitable habitat, not where we expect to see them, but where the habitat is most suitable for these species. So in sum, the suitable habitat for our iconoclast individual species may decrease, others will take over. Things will change. So how is wildlife responding to a changing climate? Again, a whole paper written on this. And I think we know that climate change directly and indirectly affects virtually all species, from our iconic moose, which may virtually be extirpated from the lower 48, to those really pesky ticks that we know are increasing. This is from just a couple days ago in the New York Times. Tick and mosquito infections are surging, and that's in part due to changing warming climate. In terms of what we know, our first principles, we know potential effects. Well, let me step back. Most of the work that we know about change in wildlife is on bird studies, and so I'm just going to focus in on that. I have some work on fish, but I don't think I'll have time to get that today to be true to the time here. But so for birds, in first principles, we would expect direct effects on physiology and reproduction, direct effects on habitat quality and fragmentation, effects on food source, including amount, type, and asynchronies of when the food is there and when the birds are coming back, differences in predator-prey relations, and pathogens and disease. So the work by the folks in this synthesis were able to show that we can say that the timing has changed. This is historically what we've already seen. Birds are returning earlier, they're breeding earlier, and they're departing later. The abundance is changing as well. In the positive, the abundance of 15 of our 25 resident species that were studied is increasing. They like this warmer weather. They're okay with it. We see variable effects on short and long-term migrants, and of course a part of that depends on what's happening in their wintering grounds. It's not just what's happening here. And we are seeing a range expansion of a lot of species. Again, 27 of 38 species are increasing their range. So this begin to look familiar to you. Use this same climatic envelope approach to look at what might happen to birds in the future. We developed statistical relationships between where the birds are now and what their climate and what their habitat is. Then we determined the future climate and habitat from the previous work that we just talked about. So we were all working with the same models. And then we projected the new distribution and abundance of birds. And I apologize for this being a table, but this is for our resident populations. And again, they're doing pretty well, or we expect them to do well. Over 50% of those we expect their abundance, their incidence to increase, and their range to increase. A little bit different story on our migrants. We have a few more of those that are declining, and kind of an equal number in changing their distribution. So a little bit different story between the migrants and the residents. Again, we expect winners and losers. We might lose some of our iconic species, such as our loon, white-throated sparrow, ruffed grouse, blackbirdian warbler, bignell's thrush, but we might gain others. increased number of pileated woodpeckers, which I know I've been seeing lately, although that's land use change as well. Cardinals, great horned owls, yellow-throated warblers, whippoorwills, the list goes on, but I think you get the point. There's winners and losers. A particular concern is high elevation birds, right, because they have nowhere to go, you know, as the climate begins to warm. And you might be aware of some of the work that's being done on the Bicknell's thrush. And this is just looking at suitable habitat for Bicknell's thrush. And you can see at about 3 degrees, they lose all suitable habitat. And that would be about where we are in a low emission scenario. So we're certainly going to lose some of these iconic species. I'm going to skip my favorite topic, which is trout and salmon, and you guys can come ask me anytime. Well, just in a nutshell, we know that there's all kinds of threats to our cold water species. Climate change impacts virtually all of these. And then we know all of these things, that climate change, increase in temperature will affect the populations. High flows is going to affect the populations. Low flows will affect the populations, and extreme events. And I could give a whole talk, in fact I did, at the Maliaket TU a little bit ago on the effect of climate change. I will just show these fish, one because they're from New Zealand, and New Zealand is very cold. But they're kind of an example. New Zealand had its warmest, driest summer on record this last year. And we were catching these beautiful rainbow and brook trout, but they were very misshapen. They had these giant heads and these long, skinny bodies, just suggesting that they were highly stressed from this climatic, very dry, very warm. Projected brook trout futures, this looks very familiar. This is where we find our brook trout now. Under a low emission scenario, you can see that we lose areas for brook trout populations. Under high emission scenarios, they're basically gone from this area. So, in sum, wildlife responds to climate change. Vulnerable species are highly specialized or restricted to critical ranges, like those high elevation ranges. And we have a lot of detailed studies primarily for bird and fish populations. So, closing statements on the science from this. Climate of the Northeast has undisputably become warmer and wetter. Climate models suggest that the climate of the Northeast will become warmer, wetter, and drier in the next 50 years. The hydrology of the region has changed. Our rivers, your Androscoggin, our Androscoggin River, it is changing and it will continue to change in the future. And that these changes in climate and hydrology affect virtually all aspects of the forests and the wildlife that they support. I would be remiss if I didn't talk a little bit about adaptation and mitigation. We're scientists, so we were really trying to synthesize the science, but it was just so clear to us that the types of adaptation that would be helpful: increase protected areas and refuges, conserve stepping stones and corridors, reduce other stresses on forests, and start practicing what we're beginning to call adaptive silviculture or adaptive wildlife management for climate change. We're trying very hard to get the concept of climate change into our management practices in the Forest Service, in USGS, in inland fishing and wildlife. Mitigation is tough. I also wear a hat where I'm a co-director of the USDA Northeast Climate Hub. We can talk about adaptation to farmers and foresters, and they get it and they want to hear about it. Problem with mitigation is you have to accept there's a problem and that we're a part of it. So it can be very difficult to talk about mitigation. However, we do anyway. So mitigation, keep forests as forests, prevent forest loss. They store a tremendous amount of carbon. Enhance the carbon storage in managed forests. We can manage forests to stuff more carbon into it. And believe it or not, China is doing this in a big way right now, and we're consulting with them to help them do that. replace fossil fuels with smart biomass. And then I always say the law of the humongous. I have 3 kids, they're adult kids, and they sometimes look at me and they go, well, what can we do? And I'm just a big believer if everybody does just a little bit, you know, walks or bikes or turns off light, you add that all up, it's the law of the humongous. It will indeed make a difference. So, science of climate change is advanced, it's getting better all the time. Strategies are available to adapt to and take advantage of climate change. We know what to do. We need rapid information exchange, things like these papers that we've been putting out, communicating to all of you great folks, and trying to think of being proactive rather than reactive in the face of a changing climate. I appreciate your patience. I'm sure I went over a little bit, but there's so much to cover. But anyway, thank you very much. And there are copies of these in the back if you would like to take one. They're also available on the internet. If you're going to take it and just put it in the trash tomorrow, please don't take it. But if you would like a copy for yourself or your organization, you're welcome to have one. Thank you very much.
We do have time for 1 or 2 questions. We are a little over our time, but yes.
One quick question. How do you define smart biomass as a fuel?
What's
How do you define smart biomass?
I think we're thinking of alternatives to fossil fuels in this. I mean, it could be biomass in the sense of harvesting our biomass, but we all know that there's some issues with that. Renewables.
I know that has problems too.
There's a lot of problems with that. In the back.
Yeah.
So on your predicted schedule there for the big nails, you're looking at 30 years before we stop seeing the big nail, or less?
It depends on whether we stay on the low or the high emission scenario. As I'm sure you guys already know, we are still happily working up the top high scenario. So that might be within 30 years. The lower scenario, which is basically very drastic reductions in fossil fuels, declines in population, might be longer. But we're going to get there, certainly in the Northeast. The problem right now is we continue to go on the highest emission scenario. We haven't gotten off that yet.
Thank you so much.
Thank you.
I'm Chris Kimball. I'm a meteorologist at the National Weather Service in Gray, Maine. I'm also the local focal point for climate at our office. So I wanted to talk a little bit about the climate in New England, some of the drivers for the climate. Once we understand those climate drivers, then we can understand how global changes may be affecting these drivers and in turn affecting climate here in New England. So for New England, we're known for our strong seasons, long, cold, snowy winters, cool, damp springs, mild summers, and then prolonged autumns. We have our frequent storm systems, nor'easters, generous precipitation throughout the year, especially compared to other parts of the world. But why? That's what I want to get into. One of the first things I want to talk about is global circulation patterns. This is what drives what we call the westerlies. This is driven by differences in heating across the globe. The tropics warm faster and more quickly than the polar regions do, and the polar regions cool. So as a result of that, you have global circulation patterns which try to distribute that heat more evenly around the world. This is largely driven by the latitude, but it's also affected by the Earth's rotation. So as I said before, right in the equator region, you see your warmest temperatures, and then at the poles, you see your colder temperatures. And so in general, you have a flow of air from the poles to the equator at the ground level and then in reverse up above the ground. But because the Earth rotates, we end up having 3 distinct circulation cells, what we call cells, where we have the northeast trade winds blowing in towards the equator. We have subtropical highs, which happen to be where most of the world's deserts are. And then from the poles, we have the polar easterlies, where airflow is coming out of the poles and then turning to the east by the Earth's rotation. And then in between, we have the westerlies, which is where you have a mixing of the cold polar air and the warm tropical air. We have lots of frontal systems that move by, sending warm air northward ahead of them and then cold air southward behind it. That's how you get the balance of heat across the globe. So again, this is a prevailing westerly flow in the mid-latitudes. This is why storm systems tend to move from west to east across our area. The jet stream drives these storm tracks, and it's why we have frequent nor'easters and other strong storms in our area. And this provides a large portion of our precipitation. This is another look at the westerlies. Again, you have the northeast trade winds down here to the south of the subtropical highs, and then the westerlies in between, where you have storm systems migrating from west to east across the country. And there are some variations in the flow. It's not straight west to east. There tends to be up and downs, troughs and ridges, and these are what bring us our changeable weather. Another driver of our climate is the Atlantic Ocean. It is a very large source of nearby moisture. This helps moderate temperature extremes a little bit, but it's also our primary source of moisture for both rain and snow. The Gulf Stream is also another factor. This is the warm air moving out of the warm water moving out of the tropics and out into the Atlantic. And this warm ocean current can affect the track and intensity of storm systems. So we often see storm systems moving up out into the Atlantic here off the coast of New England, and they feed off of this temperature gradient between the warm Gulf Stream and the colder waters over the Gulf of Maine. The Appalachian Mountains are another driver of our climate. These mountains can block the flow of air depending on the air mass. Cold, dense air will pile up on one side of the mountains, and it can be blocked or diverted by those mountains. We often see what we call cold air damming, especially on the eastern side of the mountains, where east or northeast winds will trap cold air over the coastal plain. Warm, moist air may move in over the top if you have a storm system moving in. That'll cause our freezing rain, sleet, and snow. And it's a significant factor in why we have high snow totals across Maine. And this is just a representation of the normal snowfall across our area. As for the changing climate, the assessment that I'm discussing here is taken largely from work done by the National Centers for Environmental Information and others. They also have detailed state-by-state analysis at this link. And that's what has driven most of what I have here in this presentation. So warming temperatures globally can affect some of these drivers of our weather. The first is the westerlies. Since the polar regions are warming faster than the tropics, in part due to not having as cool of nights, this can cause a weaker and meandering jet stream, since this jet stream feeds off of the temperature difference. If that temperature difference is smaller, then the jet stream is weaker, and it will often be more what we call blocky. It'll have a blocking pattern with longer periods of stagnant weather. This is an example of a blocking weather pattern. So you have a large trough here, huge ridge here through the middle of the country, and then another trough here. When the jet stream gets this highly amplified, these large troughs and ridges tend to stay in place for a long period of time. And this will cause generally stagnant weather, where you have cool conditions here in the east, wet right along the eastern edge of the trough, and then dry and warm in the ridge area. And so as these blocks occur, you can expect to see more frequent periods of wet weather and more frequent periods of dry weather. That's how you can get both droughts and floods as a possibility from climate change. As for the Atlantic Ocean and how it's affected, warmer water temperature would increase the amount of moisture that is available for precipitation causing storm systems. So this would mean wetter nor'easters, heavier rain, or even heavier snow, depending on the temperatures at the time. It's not necessarily that we have more frequent storms although that could be the case, but it's more that the storms we do have end up with more moisture in them and dropping more precipitation. Warmer temperatures generally promotes greater evaporation potential, so this is how you could get faster drying of the soils, leading to droughts more often as well. But with greater evaporation potential and warmer temperatures, the air can hold more moisture as well. So when you do get greater moist flows in from the Atlantic or the Gulf of Mexico, it increases the precipitation intensity. Some of the observed changes, some of this has been gone over already. The changes in average temperature that we're seeing are driven in large part due to nighttime temperatures not being as cold. So you see less cooling at night. And this is more dominant in the Arctic region, which is dominated by nighttime cooling in their climate regime. We've also seen greater precipitation, including more extreme precipitation events. Here's an example across Maine over the past century or more of the observed winter temperature. So you can see in general over the decades you've had a gradual increase, especially in the last few decades, in the winter temperatures. And this is particularly notable in the number of very cold nights. So this is number of nights where you fall below zero. You can see that we have fewer of these nights than we have in the past few decades. Summer temperatures. The average summer temperature is also increasing, although it's not as extreme as in winter. But notably, the number of hot days where you have temperatures above 90, those are not increasing, they're actually decreasing. And this could be in part due to increased moisture in the air, increased cloud cover. Again, our changes in temperature are largely driven by nighttime temperatures. So this is why your number of hot days aren't quite showing the same trend that everything else is. Annual precipitation is also increasing, especially in the last 2 decades. I've noticed this as well in keeping track of climate records at Portland and other places. Just in the past, we had about an 11-year period where we had a lot of heavy rain events from about 2003 to 2015 or so. And after that, we've been a lot more variable. Number of extreme precipitation events is the number of events that drop 2 inches or more of rain. That has also increased in the last couple of decades fairly dramatically. As far as what we expect for the future of the climate, generally we're expecting the trends we've seen already to continue or intensify. That includes greater frequency of heavy rainfall and flooding, which would affect the outflow along the rivers. You'd have basically a feast or famine approach when it comes to drought and floods. So you have periods of heavy rainfall, but also periods of really dry conditions as well. Snowfall would be pretty inconsistent, but generally decreasing. You do still have some extreme events. And in general, we also expect more frequent heat waves, although again, we haven't seen that quite as much yet, as the warming has primarily been driven by nighttime temperatures. As for the snowfall, we need the 3 things. We need the cold air, where the warm temperature means in generally less snowfall. But since we're increasing the moisture as well, that would mean more intense snowfall when it does fall. So that's why we're expecting, in general, more inconsistent snowfall. There's just a few climate resources that I was using in preparing this presentation. I'll be happy to answer a few questions if you guys want to. Yes?
I was just curious, I don't really understand why cooling would be less at night. What's the difference between the day and the night? What would cause that?
Well, the observed changes have been most dramatic at night. So our low temperatures have not been as cold as they have been in the past, Our high temperatures are slightly warmer, but not as warm as the nighttime temperatures are. Might not have fully understood the question. You can try again if you want.
So, well, for example, on a cloudy night, you have less radiation cooling.
Right.
Is that part of the issue, or why do nighttime?
I think that would be part of the issue. Another part is when you're talking about greenhouse gases and the effects that they have, that's a feedback issue rather than a direct issue. Therefore, that's affecting the ability of the Earth to cool. And since cooling is what's going on at night, that's when you see that most dramatically. But again, I do think that cloud cover is probably a factor as well, although it's not as well understood or tracked. Yes? I have heard that the Gulf of Maine has been warming, and there's a few possibilities for why. I'm not terribly knowledgeable about it myself. I know there's some question about lobes of warm water from the Gulf Stream having rotated into the Gulf of Maine may have helped enhance that, as well as just general warming from the warming climate. Yes?
Are you familiar with the theory that particulate air pollution could have or could be changing the nature of some of the clouds and actually keeping some of the solar energy from the Earth's surface, and so that some of the potential ill effects of global warming are actually masked right now? If we clean the air of particulate air pollution, that it will actually allow more energy in.
I haven't studied that in particular, but I would not be surprised that, you know, as you change the composition of the atmosphere, it has effects both positive and negative, and thus it'll affect the overall trend. I know that cloud cover is one that also affects incoming solar radiation as well as outgoing, and that also depends on what level the clouds are at. Yeah, it wouldn't surprise me. I mean, that's what happens when you have volcanic eruptions and other things. Yes?
I believe I've read that the Northeast is seeing a more rapid change in rising temperatures than the rest of the continent. Is that true? And if so, what would be causing that?
Since the change in temperature is driven largely by nighttime temperatures where cooling is dominant, further northern latitudes would be affected more than southern latitudes. So I'm from Tennessee originally, Memphis, Tennessee. Things aren't changing quite as dramatically down there in terms of you know, what the temperature's doing, because they're not as dominated by cooling as we are further to the north. So there would be something to that. However, you know, we just saw from her presentation that the numbers are similar across the continent and across the world, at least in our area.
See if anybody has questions for Lindsay.
Oh, were there any more questions for Lindsay?
I have one, but we'll let you go again.
Okay. All right, so I just have a few more slides. I just want to tell you a little bit more about the Citizens Climate Lobby. And this is the exciting thing about it is they have a plan for not just understanding climate change and not adapting to climate change, but also to doing something to go toward that low carbon future that's going to make a very different scenario than the one that we're on now. And basically, it's a pretty simple plan. If we want less CO2 in the atmosphere, we need to make it more expensive to put it there. And so this is the simplified version of this. There's a lot more detail, and it's very well thought through. But basically, they are proposing a carbon fee and dividend system, a nationwide system using existing bureaucracies that we have, like the Social Security and our way of taxing and tariffing at the border and so on. So using existing resources and just adding on these programs. This would be the first part of the system, which is imposing a fee on not the oil extraction itself, not the coal extraction itself, but the equivalent of how much carbon those will burn when they're emitted, when they're burned, will be emitted into the atmosphere. So for every ton of potential carbon emitted, there'll be a certain fine put on those resources right at the point of kind of entering the market. And that could be at the coal mine, it could be at the oil refineries, not every single oil well, but at the oil refineries, or at port of entry. So that's the first part. And of course, by putting that fine on carbon, that's going to, one, send a signal to the market, and that signal is going to go right up through the market. So it's going to cost more for items that use a lot of carbon to create, and less for those that are low carbon emitting processes. So, and the whole idea with the fine is that it's going to start low and just be increased on an annual basis at a regular rate that is very predictable to the market. So it's a signal that's predictable. And then, because it's going to cost you and I a bit more for not only gas at the pump, but all of the things that are made that produce CO2 in the production, all of those fees are going to be collected, and then everybody gets an equitable share. Every household in America gets an equitable share of those dividends to help offset your increased pricing. And if you live a low CO2 life, you're going to be able to put that money right in your pocket. If you don't, then it's going to help offset your additional costs. And then because our goods created in America under this system are going to cost more relative to countries that don't have a carbon fee, there's going to be an adjustment at the border, and that will offset the costs going out, and also a tariff on goods coming in from countries that don't impose a carbon fee. So that's basically the system in a nutshell, and there's been studies done on what this will do for the country and for our emissions and so on. And basically, under this program, once it's imposed, within 10 years, there'll be a 31% reduction of carbon emissions, and that is below 1990 levels. So they took the 1990 levels and said, by this, in 10 years, we'll be 31% below that, and within 20 years, we'll be 50% below those carbon levels. And in the process, we're going to have to retool our economy, and again, this is a market-based solution, so there's going to be, as I said, these market signals, and the winners are going to be production systems that do have low carbon emissions, and there's going to be 21 million jobs created in 10 years, and another 2.8 million in 20 years. And there'll also be a relative growth to our GDP as a result, studies show, and again, pretty significant growth in our economy. So it's not environment or the economy, it's environment and the economy. And then also, this is kind of a side effect in a way, but as we're reducing carbon emissions, we'll also be reducing some of those other pollutants that are going into our atmosphere that exacerbate respiratory illnesses and even shorten lives. So there'll be lives saved through this system. And then, again, we'll all be getting our dividend, and if we're wise users of that dividend, we'll be looking for goods that have been produced by people using, and companies using, lower carbon emission processes. So how does CCL go about making this happen? And it's really through helping to build the political will. They've started at the national level, but they're organized into local chapters. So we now have the newest local chapter, maybe in the country, we're very new, but definitely in Maine, and we're based in Norway. So anyone who's in driving distance to Norway who would like to get involved, you'll be getting in on the ground floor. We're all very excited about this. And we're learning how to meet effectively with Congress, and meetings are set up, and where we can talk to our congressional leaders and discuss our concerns and our nudging them toward the consideration of the carbon fee and dividend. We're learning to be more effective communicators through all forms of media, letters to the editor, op-eds, online, and we're doing outreach at various venues, and this is one of my first outreach events as representing a Citizens Climate Lobby. And one of the exciting outcomes of this is the emphasis is, again, as I said earlier, on bipartisan agreement on moving forward in this direction. Because the past has shown us that one administration might be very agreeable to reducing carbon emissions, replaced by another regime that is not so agreeable. And so we're flopping back and forth. And if we can get everybody to talk, the idea that this is not a political situation, this is a public health situation, this is a real human issue, and that we should all be able to, as Lindsay pointed out, the science is very strong. So we should take the science and we should be working together to find solutions. So they started, the Citizens Climate Lobby, when it first started back in the earlier 2000s, started asking members of Congress to join a climate solutions caucus where they would agree to at least speak across the aisle about climate change. And initially, one Republican and one Democrat agreed to join. And now, just a few years later, we're up to 36 Republicans and 36 Democrats. One member of one party cannot join the caucus without a member of the other party, so they must join together. And this is good. We're moving in a very good direction, because these across the aisle conversations about climate were not happening at all before this. So this is really good step. So in summary, this is the message that the climate is warming. It's us. It's bad. We can fix it. And this will maybe not solve the problem entirely, but it will certainly help. And this was another one of our outreach efforts in Norway. I don't know if anybody here has ever been to the Earth Day celebration in Norway, Maine, but I've never seen anything like it. It is fabulous. And we think a table would work because the activities move from one end of town to the other, and they have a parade, and there's all kinds of things going on. So instead of a table, we had the sandwich board, and I just had a messenger bag full of literature, and it was a lot of fun, and we got a lot more interest for our upcoming meeting. So again, if any of you would like to join us, pick up one of these invitations and at least learn more about it. And we're going to have our official training on June 24th, at which time we will become an official chapter. I don't know if we have to raise our hands or whatever, but we're going to become a chapter. So again, get in on the ground floor, and I think you may be, for those of you who are concerned about climate change as I have been, you'll sleep better for it. So again, thanks for having me here, and it's been a delight.